The topic for this talk is where physics came from. How did physics come to be a subject by itself? If I ask an audience that, a common response will say, well, people wondered how the universe came to be, how the universe began, how it ended. That's how physics came to be. Well, it's true, people have always wondered, but that's not how physics came to be. Physics began a long time ago, you know, the Greeks. How long ago did the Greeks live? Well, 2,000 years ago to the time of the Romans. And if anybody in those days wondered about how the universe came to be, they thought that the province of that answer was theology, certainly not physics. Say, well, maybe people wondered what matter was. And indeed, maybe some people wondered what matter was. But those were just a few people. That's an academic thing. That's maybe how a university works nowadays. But physics did not begin in universities. Physics began, all important things come from something practical. It means people want something. What do they want? Well, it turns out it's awful hard. So if we want to know where physics comes from, we should say, hey, physics, do you have any sisters or brothers? The sisters and brothers are chemistry and astronomy. And now we can say, well, where did they come from? All of these things come because there is a problem, because people want something. What do they want? Let's take astronomy. To know the names of the stars? No, they don't want to know the names of the stars. To find out what they want, maybe it's best to go back and think about what is astronomy? What is the old name for astronomy? Astrology. What do astrologers want? Astrologers want to tell the future. It's a very wonderful thing to be able to tell the future. A very desirable thing. But today, to know the future, there is something of enormous value. And the astrologers thought that somehow, by knowing about the stars, they could tell the future. You see, the problem was the astrologers believed that we on Earth are somehow controlled by the stars and the planets and the sun and the moon as they move around in the sky. And they believed that if somehow you could figure out where Mars would be 3 months from today, maybe you could figure out where you would be 3 months from today if you were controlled by Mars. So that was the practical problem. Now there's something about these problems. These problems, it turns out, that get a science started can't be easy problems. If the problem is an easy problem, you solve it right away. And after it's solved, that's it, you go on to something else. On the other hand, the problem cannot be impossibly difficult. Because if the problem is impossibly difficult and you work on it and you make absolutely no progress, and your friend, and he works on the problem, and he makes absolutely no progress, and maybe his son comes after him, and he also devotes time to thinking about the problem, and he makes absolutely no progress on the problem, then in that case, very soon, people will be frustrated and they will quit. So these problems that start sciences have to be problems that are not impossibly hard to make progress on, but they also cannot be problems that can be solved very easily. It has to be just a certain kind of a problem. Let me explain. What is music? Let's talk about music for a minute. Supposing you have a noise like this. Boom, 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 boom. Well, you can tell what's coming next. Boom. Is that music? Most people would not think that's music, though I hear some people in automobiles passing me on the street that seem to think that's music. But the majority opinion, I think, is that boom, boom, boom is not music. Why is it not music? There's a pattern there, yes, but the pattern is too obvious. It's too simple. You know what's coming next. Now let me give you something else where the pattern is not at all obvious. And you say, boom, boom, bang, ding, ding-a-ling-dong. Well, is that music? Well, again, there are a few people that would say that is modern academic music. But I think, again, the majority opinion is that that is not music. Why is that not music? It is because the pattern, if it is there, it is impossible to discern. What makes music attractive is that there is a pattern, but that the pattern is not obvious. You can get the pattern, but it's just on the limit of your ability to get. And that's what constitutes music. And so it is with these sciences. Well, we talked a little bit about astronomy, the problem that got astronomy started. What is the problem that got chemistry started? What's the old name for chemistry? Alchemy. What did alchemists want? Alchemists wanted gold. They had an idea that you could make things that weren't gold into gold. What a crazy idea. These people must have been very stupid in those days. How stupid they were to think that you could make gold out of things that weren't gold. Everybody knows that you can't do that. Why, if you could do it, everybody would be doing it. Well, you mustn't think that these people that lived a long time ago were stupid. But nonetheless, they weren't stupid, because now the people that can afford to Levi's pay even more to wear Levi's that have holes in them. You know, the Levi's that have holes in them cost more than ordinary Levi's. So who's stupid? But anyway, these old people who thought about these things, the same people who thought about alchemy, also thought about all these theorems in geometry. You know, there's a theorem in geometry called the theorem of Pythagoras, and it has to do with right triangles. Right triangle, that's a triangle with a square angle. And if you build a square here, and you build a square here, and you build a square here, I know, then if you take this square, A, and this square, B, and you add them together, you'll get this square over here. They not only discovered that, these old people not only discovered that, but they proved it. So these people were very clever people to figure out things like that, not only to discover them, but to prove them. You have to have the highest respect for these people who thought that you could make gold out of stuff that was not gold. Well, still, why did they think that? Don't you know you don't get something for nothing? That's a basic principle of the universe. They noticed that you can make things out of other things, and you can change the nature of things entirely. You know how you make soap? What two things you mix together? First of all, you take lard, grease, the drippings from when you cook bacon. And you know what the other half is? When you have a fire, what's left after the fire is soot and ashes. You take the ashes, the white ashes that are left after you burn wood. Those are the two most dirty things in the world. If you ask, which would you rather have to get your face into, some dirty soot or some dirty lard? You take those two nasty things and you mix them together in the right way, and you know what you come up with? Soap. It's amazing. You come up with something entirely different than you go in with. You go in with these two nasty things, and you come out with something that is used for cleaning. And the ancient people knew stuff like that. And they said, damn it, if you can make clean stuff out of dirty stuff, then there should be nothing to making gold, because look, here's all you do to make gold. It's real simple. Now, what is gold? Gold is yellow and heavy. Isn't that right? I think gold is real heavy if you've ever handled a piece of gold, and it's real yellow. And if you've also handled it, it's very soft, can bend gold. Some people advertise that their coins are pure gold, but a real circulated coin, like the American Eagle or the Krugerrand, a real serious gold coin would never be made of pure gold because it's too soft. You take something that's soft and yellow and you want it to be heavy, so what do you take? You take lead and you take sulfur. Why do you take sulfur? Because it's yellow, and this is heavy, and this is heavy and soft, and they should come together and make gold. It's easier than making soap. The only thing is it doesn't work so easy that way. But the point is that in their heart, people felt that it had to work, and they also discovered all kinds of strange things were discovered, like phosphorus and whatnot, by playing around with various things and trying to make, if not this combination, then some other combination, trying to make gold. And though they never found out how to make gold through the process of chemistry, nonetheless, all kinds of things were discovered. All the knowledge we have in chemistry was discovered as a result of starting to do this. Later on, they realized they could never do this, but it was worthwhile trying to do other things. There's another side of this story that I should tell you too. about why people wanted to learn how to make gold. There was a feeling that the process of making gold, there was another way of looking at gold. Most metal on the earth was corruptible. That if you have iron, it will rust. If you have silver, it will tarnish. Copper will tarnish. Lead reacts with various things. In fact, everything, not only metals, but wood, most everything that people have, water evaporates, everything becomes corruptible in the world. But the ancient people knew one thing that was incorruptible. That is, it would not tarnish, it would not rust, it would last forever. And that is gold. The reason for that is chemically that gold doesn't react with other things very easily. That wasn't the way they put it. They felt that there was something heavenly about gold, that it stayed by itself. They had an idea, if they could take ordinary things, like if you could take iron and take the corruption out of it, what would be left would be the pure gold, the thing that God put in. Now, of course, that was an interesting idea. If it would have worked, it would have been a way to make gold, but it would have been useful for something else too, and it would have had an even greater use. Because the same process that could be used for decorrupting iron and turning iron into gold could also be used for medicine. After all, people get sick. You discovered a process for taking the corruption out of lead or iron. You could also conceivably use that same process for taking the corruption out of human beings, and that would be a way to have medicine. Therefore, there's a practical side to making gold. Two things are interesting about that. First of all, that idea of medicine is still around, but also it's the same thing that scientists use. Whenever scientists are working on some big process like going into space or some nuclear experiment, they say, but because of this, some little spin-off from this will lead to a cure for cancer. So that's the problem that started chemistry. And of course, nobody ever did it, but nonetheless, you could make startling discoveries if you played around in a systematic way, boiled things, cooked things. You discovered all kinds of interesting processes. And now it's time that I come back to talk about physics. What is the problem that got physics started? The ancient people wanted to find a perpetual mobium, the old-fashioned, elegant way of saying they wanted to find a perpetual motion machine. Not as a toy, but as a working machine. Problem that all of us have is to do work. You got to buy electricity, or you got to buy gasoline. But everybody always says, there's a battery that will run forever. It's just that the electric company or the gasoline company doesn't want you to know about it. But if you got this battery, it would run forever. And of course, the reason is that once you had this thing, you wouldn't have to keep paying for gasoline and electricity. In the olden days, they had an ox or a mule or a water buffalo, and they had to feed it, or you have to work yourself. So if you could find a machine that would somehow keep on doing work without being fed, that would be a wonderful thing. Why in the heck did people ever believe? What made people believe that such a thing was possible? Again, it's getting something for nothing. Where did the idea for such a thing come from? The idea began with just technical inventions. Probably at the very beginning, when people were still not very civilized, if you wanted to get a drink of water, you had to go down to the creek and stick your mouth down in the water and suck up some water. And everybody who wanted to go up in the tree and get some bananas, if you wanted bananas, you had to go up in the tree to do it. At a certain phase in civilization, and this must have been a huge advancement if you think about it, that there must have been some organizer. One guy must have said, hey, Joe, you go down to the creek and you bring back water for yourself and for Billy. And Billy, you go up the ladder there, up into the tree, and you bring bananas back for yourself and for Joe, who's going to get you water. You see what a great thing. Then everybody doesn't have to do everything. Now, as soon as you begin to do work like that, you have to bring some water for somebody else. And the first invention was probably to bring the water in your hands. You had to carry back the water for Joe and for Billy. It's a hell of a thing. It's not too good because you can't carry much water and it leaks. And then people made the first wonderful high technology invention. They made a basket, maybe a basket with mud on it so the water couldn't leak out. And then they made clay pots. And the clay pots were really great because if you had a clay pot, you could bring water up from the creek and you didn't have to bring it up in your hands leaking. It was a fantastic technological advance. But it didn't end there. After a clay pot came along, Then people discovered, well, way down, you can climb down yourself, and then you have to climb out yourself. And then somebody said, look, I got this other idea. We'll make this thing called a rope. With a rope, that's a great invention. You can just send the bucket down by itself, and you don't have to go down. Then you can pull the rope up, and the bucket full of water will come up without you going down to get it. And then somebody else made an invention that instead of having the rope go through your hands, you can put the rope on a wheel, and you can bring the rope up with a crank, and then you can send the rope back down again with a crank. And then somebody else made an invention. They said, look, if you put some bacon grease on the wheel, it turns a lot easier. Wow, lubrication. And so what is the consequence of this whole series of inventions? It makes it possible to get the water up from the creek or from the well easier and easier and easier. Each invention makes it less work to get the water up. Now, you don't have to be all that smart. You can just be a tiny bit smart and a bit of a dreamer and close your eyes and think. In each generation, we make an invention that makes it easier to get the water out of the creek. Maybe sooner or later, somebody will come along and make an invention where you can get it out. You don't have to do any work at all. It's easy to get the idea that you can make things that will run better and better and better. But once you started it, this machine would run on and on and on. And of course, again, you say, well, why in the heck would people believe that you can get something for nothing? I see your stories. Your stories are believable. But after a while, by the time you got people who were smart enough to understand Pythagoras' theorem, the fact that nobody has done it or got near to it makes it kind of questionable. Let me talk about nobody's done it, nobody's got near to it. Are there no perpetual motion machines? What about the Earth spinning in space? Isn't the Earth spinning a perpetual motion machine? The answer is yes. It turns out that there are actually two kinds of perpetual motion machines. There's one kind of perpetual motion machine that's like a frictionless wheel. A frictionless wheel will spin forever providing you don't touch it. In other words, you can't make it do any work for you, because as soon as you put a pulley on it and attached it to your washing machine, or put a pulley on it and attached it to a pump, or put a pulley on it and attach it to an electric generator, all those things put a force on it and they would bring the wheel to a stop. But it's true, if you can have 100% lubrication, you can start a wheel and the wheel will spin forever. And there are examples of superfluids and wheels, or planets going around the sun in empty space, or even the electrons spinning around the atoms, and they go on forever. But the reason is that they're frictionless and you can't touch them. You can't take any power out of them. They will run only so long as you leave them alone. And those things are called perpetual motion machines of the first kind. But to be practical and useful, what you want is a perpetual motion machine of the second kind. That's a machine that will turn and turn and turn. And even when you put a belt and a pulley on it and you make it do work, and now it's not only turning, but it's dragging something with it, like pulling a train behind it, it will keep on going, unabated, without any fuel, doing work, pulling something. That's the kind, a perpetual motion machine of the second kind. You can realize that the kind that these practical people wanted in the olden days was a perpetual motion machine of the second kind, so it would crank out some work. Why did they persist in thinking that there was still a possibility of it? I'm going to show you why right now. What was in their mind that made them think it might be possible? And it's a very impressive thing that I'm going to show you. I still remember where my father took me. He took me to a playground in San Francisco, and this is what he showed me. It was a seesaw. My father sat at this end of it, like so. I was a little guy at that time. I sat at this end. The amazing thing was that even though my father must have weighed, I don't know, 150 pounds, and maybe I weighed 50 pounds, I balanced my father. What do you think of that? Is that picture drawn right? You notice the picture? You're right. The picture's not drawn right, is it? It's supposed to be put this thing will work if I put the thing over there. I did that on purpose. When you come into a physics class, you don't know zero physics. You see, you knew that right away. You saw I drew that wrong right away. You know one heck of a lot about physics, and of course you got a lot of ideas about how the world works. And one of the really important things is to see that the things you already know about physics correspond to the theory that I'm going to tell you about. Now, a lot of people think what you learn in class is one world and you just memorize it for the teacher and spit it out or recite it on the problems, but that's not real physics. To really understand it, it has to fit with the outside world. And if it doesn't fit with the outside world, then you have to, first of all, ask the teacher. Maybe the teacher won't be able to help you, but you have to pursue it down. And sometimes it's quite a bit of work to see that the things in the outside world actually do correspond with the theoretical things. It just can't, you can't say black is white one day and white is white the next day. There really is a right way of understanding it. Here's the seesaw drawn the right way. The amazing thing about this, on the inside of this side, what are you putting into here? You're putting in, on this side, 50 pounds of force. That's what you're putting in. What's coming out on my father's side is 150 pounds of force. You surely are getting something for nothing if you can put in 50 pounds here and come out with 150 pounds. That's getting something for nothing, and everybody knows that it works, that a seesaw works. You can get something for nothing in physics, and here's an example of it. Now I want to talk a little bit about astrology, which was the original problem of astronomy. If we can somehow tell where the planets will be in the future, then we can tell where we will be in the future, because there's this idea that we are controlled by the sun and the moon and the stars and the planets. Now let me tell you a little bit about how the sky works so you can appreciate the problem in detail. If you look up at the sky, you'll see that there are certain stars in the sky tonight, and the stars that you see in the sky tonight have certain positions. And if you come back tomorrow night, the stars, and you look up again about the same time of night, the stars will have the same positions. And if you look up another night, the stars will have the same positions. And even without having any experience, you can know that it's true because these stars have names, like the Big Dipper or Orion, which means that a certain group of stars looks like the Big Dipper. Now, if the stars moved around, they might look like the Big Dipper tonight, but then in a few nights from tonight, they wouldn't look like the Dipper anymore. And the fact that they keep on looking the same way, the fact that these names go on means that the stars have the same positions. When I say they stay in the same positions, I mean there's a certain arrangement of stars in the sky, just like the sun moves across the sky and the sun rises and the sun sets. All the stars, all the constellations move across the sky too. So I mean, up comes Pegasus and then up comes Orion, and they move across the sky. Well, if you see the sun rise, roughly 12 hours later, the sun will set. Same is true of a star. If you see a star rising, about 12 hours later, that star will set. Not only will that star set, but the whole constellation that it's in will come up and come down. That's the way it is for almost all the stars in the sky, except there are a few things in the sky that look like stars, but they're not. They have this peculiar characteristic. One day you'll look and you'll see the constellation of Orion. Orion looks like this. See, he's a hunter. He has a belt, 3 stars in the belt, and this is supposed to be his sword. Then he's got some more stars out here for shoulders and arms and whatnot. But in addition to all this, over here there might be an extra star. And then after a while, you'll look, this star won't be there anymore. It'll move over here. And then if you look, it won't be there anymore. It'll move over here. And then if you won't look, it won't be there anymore. It'll move over here. And then it won't be there anymore. It'll move over here. These stars wander around in the sky. And they were given the name planet. And I believe that planet is a Greek word that literally means wanderer. That's what they were. They were wandering stars. And there were a few of them. Let's see. There was Mercury, and there was Venus, Mars, Jupiter, and Saturn. These things wandered around. Now, they didn't wander around. It turned out that they wandered around the sky. They all moved gradually to the east. If they keep on moving to the east, since the dome of the sky is round, if you keep on going to the east, to the east, to the east on a sphere, pretty soon you'll go around and come back to the west. They'll make one complete circuit through all the constellations, actually move through a certain part of the sky, and they'd get all the way around in a certain amount of time. And in fact, if you watched for a while, you could find that the one Mars would get around in about 2-3 years. It would make it all the way around. And the one Jupiter, it would make it all the way around in about 12 or 13 years. And the one Saturn, it would make it all the way around the sky and came back in about 30 years. If you felt that you were, say, controlled by Jupiter, if you were born and Jupiter was in a certain constellation, and then little by little by little it would move around, and maybe when it was halfway around from where it was when you were born, something important would happen in your life. And when it was all the way around, something would happen important in your life. And so you could tell exactly when those important things were going to happen in your life. And all you had to do was be able to know exactly when it was going to happen. Now you think, well, that's pretty easy. This is a real easy problem, because we know that Jupiter is going to make one complete trip around the sky in 12 years, and therefore we can figure it's going to go 1/12 of the way in 1 year. And we can see where it is and figure out what 1/12 of a complete circle is. As you'd say mathematically, what is 1/12 of 360 degrees? You could figure how much further to the east Jupiter would be in 1 year. And in fact, that works pretty well. You can do that roughly. You can make progress by thinking that way. But Jupiter got a few tricks up its sleeve. It turns out that Jupiter just doesn't move smoothly to the east. Now, as soon as you begin to think you understand what it's going to do, Jupiter will go to the east and move smoothly, and then it will come to an abrupt stop. And for a month or so, it'll just stand there in the sky. Just stand there. And then it will keep on going. And you think, well, okay, now I know that every so often Jupiter stands still in the sky, so what I can do is I'll allow for that. You watch it. Now, I remember what happened. Every December it stands still in the sky. So along comes next December. Well, next December, it doesn't stand still in the sky. January, it not only stands still in the sky, but it begins to go the wrong direction. It actually goes backwards a little bit to the west. And then it stops and it goes to the east again. So, holy cow, holy cow. I didn't expect that. So every so often Jupiter stops in the sky, and then every so often it actually goes backwards in the sky, and you think after a while maybe you got that figured out. And then you look at Jupiter again, it comes along, and instead of coming to it not only comes to a stop, it not only goes backwards, but this time it moves a little bit to the north, not much to the north, and then it goes back to the south again, and then it begins going on to the east. In other words, it not only goes backwards and then goes forward, but sometime it actually goes backwards and then up and then forward. It makes a loop like this in the sky. So you have a thing that's gradually moving to the east, and it is going to make a round trip, making one complete trip all around the sky in about 12 years. But on the way, it does all these weird little things that you try to figure out that keep on screwing up your predictions. And the moon is another one. If you try to tell where the moon's going to be, it does, but on the way it goes fast and slow and goes here and there. It's got one heck of a bunch of tricks. So you can see that this is the kind of a problem that you can work on, and you can make progress. You can discover some of its tricks. And then somebody else can come along after you, and they can study it some more, and they can discover some more of its tricks. And then the people after that person can come along, and each person can come along and discover some new tricks in this. And you can see how this is almost the exact formula that I gave for the kind of a problem that's not impossibly hard, but also not very easy, where many generations of people come and work on it. That's how it comes to be a science. You can almost see, by seeing the way that people used to think about it in the olden days. The old way of explaining this was to say, the Earth is in the center of the world, and there is a big wheel out here in space. Now, this big wheel is Jupiter, and out here are the stars. And this big wheel that Jupiter's on turns around the Earth, and it goes around once in 12 years. But of course, that won't quite account for its motion. Now you could say, well, this wheel stops and begins to turn backwards every so often, but the old-time people wouldn't like that, because they believed that if something began turning in heaven, that it had to turn smoothly and continuously forever. But they found a way around it. They said, I know how to explain this. What they did is they say, on this wheel is another wheel, and on this wheel is Jupiter. Now look at what this is going to do. This wheel turns this way, but this wheel will turn this way. So now Jupiter would move forward, but when this part of the wheel goes here, look which way Jupiter will be going here. It will be going backwards. See how that will be able to make Jupiter Here it will go forwards, this speed plus this speed. Here it will go backwards, this speed minus this speed. So speed will change. And then you discover that Jupiter does something else that's weirder still. And so the next scientist that comes along says, Jupiter is not on this wheel. There's another wheel here like this that turns in a certain way. And Jupiter is on this wheel here. And this is Jupiter right here. And there's Jupiter. And you can see how you build on this and build on it and build on it. And that's the formula by which astrology grew. And that's the formula by which many sciences grow. As you know, to end one of these talks with a question, a very serious question. This is not a school question. This is a question that bothered scientists. I would say it bothered them from the time of the Greeks, and it probably wasn't clearly answered up until the time of Galileo. I don't even think Galileo could clearly answer this question, though he could come pretty close. By the time of Newton, the answer was clearly known. And here is the question. The reason people want a perpetual motion machine is because they want to do work. But now comes the question of what is work? That's part of the question, what is work? The question is sharper than that. Here is the lever again. And you remember with the lever, if you put in a certain amount of force here, say you put in 5 pounds here on this end will push up with a certain force which will be much greater than 5 pounds. It's 10, maybe 15 pounds. You'll get 15 pounds of force will come out of here. What is the difference between force and work? Supposing I say, well, I know what work is. Work is force. Force is work. Force is energy. Energy is work. Is force work? Yes or no? And if the answer is no, then what is the difference between force and work? And that's what I want you to think about.